I'm looking forward to this next talk because it says must die. You know, it's very science fiction-y. Yeah. Our next speaker is my pal Rick Wagner from the San Diego Supercomputing Center. He's the HPC Systems Manager at the San Diego Supercomputer Center, where he has technical and operational responsibility for two of the National Science Foundation-funded extreme science and engineering discovery environment exceed HPC clusters, Gordon and Comet, and SDSC's Data Oasis parallel file systems. Rick's other interests include motorcycles, supersonic turbulence, and teaching high school and college students about distributed computing using Raspberry Pis. I'm not going to mention that you're a Marvel Comics fan. Oh, hell, I just did. Ladies and gentlemen, Rick Wagner.
All right. As always, thank you, Steve. First, I apologize. I picked up some congestion, so I'm just making Steve sound even better in comparison. Second apology is so the names on here are myself and the developer in my group. By the way, if you have a systems team, you need a developer in the group. Tell your boss. I'll tell your boss. But the third name that should be on here is Haisong Kai. He's our storage engineer. He's the one who had to give a lot of feedback on the tool and the performance. So if you have questions about using this in practice, please touch base with him. The second thing I'll point out for those of you who like to jump ahead and don't want to wait until the reveal at the end, if you go to github.com/SDSC and look for the repo that's lustre-data-mover, you can start taking a look at the code right now and ignoring me. So I mentioned this in my last year's presentation where I talked about our deployment of the second generation of our Data Oasis file system, that we had this awesome idea to consolidate a bunch of our existing Generation 1 Data Oasis servers into what we called durable storage. This is a disaster recovery replica that is not available to users. Not quite HSM, we're not dynamically moving data back and forth to grow capacity. It's the oh shit file system, because people are human and MemDSs can fail, and if you've got several years of work on a file system, maybe you should try to back it up. So to do this, we had to do many things. One is consolidate all of our old servers. Problem is, some of those servers and file systems have data on it that people care about quite a bit. We allocate and quota a file system for projects, and that data has been around now for 4 years, maybe 5, and now it's going to have another 4 to 5 years. So we're trying to keep things as easy as possible for the users. So when you've got a petabyte and you're going to pick it up and put it somewhere else as part of your plan, you need a tool. Then once that project space was moved over, we needed a background process to take it without interfering with production and replicate it in the background back to the durable storage. So, and as it says in the title, rsync is not sufficient. rsync is designed to work on a single server and build everything in memory, and John White's notes yesterday just reinforces other people's comments. In particular, if you go back to 2013, Mark Stearman gave a great presentation on the extreme frustrations he did, that no matter how smart he got about trying to sort the data, find the data, push the data, dive into things, on Sequoia for migration experience, he was kind of overwhelmed. And Mark's a smart guy, and he did a lot of good stuff, and it still was too challenging. So you can't rsync a petabyte unless you want to take forever. So what can we do? So there was a meeting, and I kind of lost it politely with my team. I'm like, has anyone here heard of recursion? There are assumptions you can make about a file system. We have 1,000 to 3,000 compute nodes that are available to us at any given time to do this work. We have a parallel file system. Why don't we have a parallel tool? So, and rather than try and assume anything about the structure, we know our file systems are crazy complicated. And there's deep directory trees, and there's big files. So you've got to go in and treat each little directory as its own thing. So what we developed is a recursive worker service. basically lightweight tasks that can follow instructions. So if you think about the little graph up in the upper right-hand corner as being an example of the full file system, you know, you could try and build that tree in memory, like rsync does, and then go down and work on it. Or you can break it up into little pieces, and everybody can work on their little piece. So you see the two little pieces at the bottom, you come in from the top, and you are only concerned about what is in that directory. And even then, you can break it up even further, and you pass it on to someone else. So rooted directed acyclic graphs. This is the thing that makes things easier. There's a top of it, and nothing connects across it. So you can break up each little piece, and things work fine. And then we just decide what the workers are doing. So what are our, I'm sure, yeah, okay. So our building blocks, Lustre Clients. So when we have big transfers, when we were taking and we had to actually clone our scratch file system because we were concerned about stability and we really wanted to do a data migration as part of the upgrade, we use compute nodes, right? I have lots of them. I can take 5% of the system out of service temporarily and have 100 machines. So I can have lots and lots of workers, and I can usually get away with that temporarily for critical need. We also have just 4 stupid little machines with single 10 gig attached Ethernet devices that do the background migration. Not very expensive, constantly working, moving things along. So we have some Lustre clients. There's nothing magical about them. We use RabbitMQ because you've got to store this to-do list. And RabbitMQ is based off AMQP, which is a reliable message transport service. It's really fast, and the messages get to where you want them to go. So think of it as text messages, which can make your life a lot easier when it comes to administration. I'm a crazy fan of RabbitMQ. Celery takes RabbitMQ and makes it even better because it lets you build workflows via your scripts. So you have this idea of things that you want to do, and what do you do if it fails? Well, I want it to report, or if this event occurs, I want it to do this. So Celery, pretty awesome, and then a handful of bash scripts. Those of you that have already gotten into the source code can see there's not a lot there. There's some Python, and there's some bash scripts. So this is the architecture. If you think about it from the top, you've got a RabbitMQ server that's getting messages all the time. There are clients, so these can be compute nodes or our dumb workers, and they're running a certain number of tasks. Basically, you're either handling folders or you're handling files, and you're coming from a source file system to a target file system. By the way, we tend to mount the source as read-only because the whole idea here is to preserve data. And sort of empirically, what we found is rather than having a single type of worker that looks at files and looks at directories, it was better to break it in half. We can limit the number of things that are doing directory lookups versus the number of things that are actively looking at files and copying them. That's just something we found through working on it. And the number of workers you have can be scaled and can grow or be torn down because we handle signals, and you can actually throttle back and throttle up. So unlike some of the MPI copy tools, you're not fixed on a single size, and the RabbitMQ server is keeping the to-do list, even if you're changing the number of workers dynamically. So pretty useful. On a single node, you've got the RabbitMQ server sitting there across the network, and then you've got 2 Celery managers, one that's handling the file workers and one that's handling the folder workers, and then you just choose how many you have. I don't know why Dima was very concerned about this thing, about the workers pool and the multi-threading package, but threads are cool. So because we're doing this on live systems, and we're basically going through the POSIX layer, even though we use a lot of Lustre commands, you have to do things in phases because the data is live and it's changing continuously. So what we'll do in the background is we'll copy data, and then we'll take a downtime and come along and do a synchronization on the assumption that we've done most of the work and the downtime doesn't have to take very long. In the case of our standard replication, we just sort of continuously do this and we never get fully synchronized. But our goal with that is not to have an exact replica. Like I said, it's about, oh crap, is if I say to you, I lost your last week's data, but I didn't lose the last 6 years. I hope that's better than losing it completely. So it's a trade-off. Each pass can have a couple of phases. You do a copy, then you come back around and you look for files that have been moved or deleted. You delete them only from the target, and then you go in and fix your M times. And then you do, if you take a downtime, you run all 3 of them. The algorithm is pretty straightforward. Assuming the yellow is a message and the blue is an action taken by a worker, the first thing you do is a worker is told to scan directory A. It verifies that A exists on the source. If it does, it's going to create it on the target. So then it's going to look at the files and it's going to send a message. It doesn't move the files. It immediately sends a message to get someone else working. And then it looks at the number of directories and sends messages, and then it goes back on its business and picks up the next message. The next worker gets the same thing. Looks at AA, creates it if it needs to, and then looks for the files, sends a message, and then it keeps going. And the reason you're seeing multiple LS like ABA and ABB is they're independent messages. So there's one message per directory, and then the number of files are grouped based on how you tune it. So when we get to this directory with lots and lots of files, there will be several messages sent chunking up the files so that each worker handles a reasonable number. Again, it's a tunable. We use 100. We'll sort of go through these. These are for people who really want to see details on it. We check the stripe. We check the stripe for the MDT because we run DNE, and we check the stripe for the number of OSTs. And we use some LFS commands to find, stuff like that. We try to be as efficient as possible. We're using the metadata servers and the MDTs as our databases for the state of the file system rather than some external one. And then you go along and you basically steal what rsync already does because you only need some of rsync's features. So is this file newer than this one? Is the time changed? Is the size changed? Did some other stat change? If so, then I'm going to copy it or overwrite it. If it's a symlink, copy the symlink. Same thing on delete. You're looking at the source. If something is gone from the source but exists on the destination, delete it from the destination. It must have been moved or deleted since your last pass. And then go through, do an mtime check. Clean it up, try and make this destination or target file system look as much like the previous one as possible. So along the way, we wanted to throw in some extra parameters. So we have an exception list, just some basic pattern matching. Some users have pathological directory trees. She's very nice. She's a very good scientist, but it kills us. So we try to limit things. We'll often identify those cases and actually contact the user and say, is this data critical? If it is, we will copy it, but if we can avoid it, we will. We also can avoid recently changed files because you don't want to copy files unnecessarily. So if the file is newer than a day, we'll leave it sitting around and wait to see if it stays. Maybe it's just a temporary file. And likewise, as we were doing this migration between older storage to newer storage, but preserving the file system, we could implement a purge. So one of our clusters has a 90-day purge policy. So if your data was older than 90 days, it didn't get moved. We use root squash in various ways. Typically, if we're doing a big copy, we'll de-root squash all of the clients. But if sometimes we will leave them root squashed, and then we have a single specialized node that will handle things if we run into permissions issues. And it reports to Graphite, because Graphite is awesome. Graphite is so awesome that if you don't tell it to keep your stats around, it will gladly erase them because that's what it's told to do. So I don't have good numbers on the big copy experiences where we were seeing lots and lots of bandwidth and many, many files. So when we did the big 1 petabyte, we would see peaks of up to and over 15 gigabytes a second off of 24 nodes. Clusters have way more bandwidth than they need to storage, and it's rarely utilized. We're trying to drive up the amount of files we can move and the amount of bandwidth we can move at the same time. It doesn't always work, but at times it feels really satisfying when you see that bandwidth getting consumed. RabbitMQ in memory. All the messages are in memory, which is a trade-off between performance and being able to start over again. So if the RabbitMQ server went down, we'd have to start from the beginning. But we can handle thousands of messages per second. For our day-to-day weekly routine of moving data around, we have those 4 nodes, single 10 gig, single socket, and it can move the delta for a week. If the users are active on the project storage, within about 3 days, we can have copied all the changed and new files. So the goal is to be within about a week, and we surpass that. So we can get everything copied, and you can see the files per second go up to about 3,000 at times, and then kind of drop down, and then bandwidth peaks up and down depending on what kind of files it's looking at. The delete pass, which is a lot of just metadata activity, takes about a day to crawl through a petabyte. And these are really messy file systems. I gave a presentation at Exceed on the realities of this. The cumulative distribution function for our file systems is oddly very small, very few large files. We are in the long tail and the large user community for HPC. So I mentioned that we have two types of workers, folders and file workers. And that's kind of a tunable. That's something we said to estimate how to balance things. Unfortunately, it is still hard to build your file lists and copy small files and in the background be moving large files. And the reason for that is if somebody has 1 million files in a directory, and they will, you have to run like 10,000 workers to be able to handle all of them. And we don't run 10,000 workers, we run maybe up to 100. So eventually, since you're doing a depth-first recursion, you are going to hit that directory and you're going to spend a lot of time in there, even though you've parallelized the copy. So one of the things I was talking with Robert Reed, he pointed out, once we've made the pass, we actually do have insight into the structure of the file system. We know something about the users. And if you make an assumption that users with large files last week are going to have large files next week, perhaps you can prioritize the transfers and get those big files going in the background and use your bandwidth earlier. So it's a nice thing is this is easy to implement. Probably will. So wrapping up, thinking about what we're going to do next. Comet's in production for about the next 4 years. We are going to use this tool. It's going to be maintained. It may be improved. This basic thing that it does is pretty dumb. It lists things, it copies things, it deletes things, it changes metadata. It could be abstracted to other things. We've used it with a straight POSIX interface to ZFS. We tried to screw around with the WAN. The latency got in the way, but perhaps you could interface with some other tool like BBFTP or Netcat to shoot the data across the wire if you can deal with the bandwidth delay product. Easy to put in checksums. So there are other things this could be good for, but at the moment, it's not too bad for just taking a large file system and putting it over there. When we did our last big transfer for the project storage, we had a 36-hour downtime to do the synchronization for 1 petabyte. I'd hoped for it to be 24 hours. I think if we did it again, we could balance it, but you have to watch out for metadata server load. That's kind of your limit, is are you blowing up the source or target metadata server? Please, I already pointed you guys to this. Take a look. It's pretty basic documentation. It's new code. We use it in production, but needs broader testing, needs some better documentation, and seriously, the name is as dumb as the tool. So if somebody's got suggestions, maybe the first person that issues a pull request with a bug fix, you get the right to name the tool. And if you find something, we are going to fix it because this is our users' data, and that's about the most precious thing that I have. I can lose compute nodes anytime, but if I lose the data, I lose your work. So, thank you very much.
So you mentioned be careful of blowing up your metadata server. So fundamentally, you're taking a scan of every file in the file system. You're walking the namespace. Yes, you're breaking it up into little pieces, so that keeps in memory. That's good. But you're still, for every file, you're contacting the metadata server, reading its metadata attributes, contacting the target server, reading its metadata attributes, comparing them. But yet there exists a mechanism to just look at the files that have changed, right? The changelog. So have you thought about using the changelog as the input source to drive your RabbitMQ, your queue of things to move?
I did, and that's the first thing we tried. And then I was like, look, the changelog works, but how do I parallelize it? How do I distribute the changelog to multiple hosts so that they can be looking at different parts of the file system? I wanted scalable because when you have a large problem, you want to find a way to break it up. And I don't have to do anything on my metadata server. And for me, there's a comfort level saying, I'm coming through either liblustre API or the POSIX layer. So rather than do any changes on my metadata server or export the changelog, I can just come in through the client layer. And then it's flexible if I have to deal with a different file system along the way.
So would RabbitMQ, would that, in other words, if you directed the changelog directly into a message queue, would that provide your distribution of?
It absolutely would. That's a good suggestion. Yes, if the changelog went there, because you can literally text from your phone to the RabbitMQ server with a directory name and kick off the process. Dima loves doing that. He's got he just gets out his client, he's like, boom, /foo, and off it goes. So that's all it's required is training something to read the changelog and do it. Yeah.
So there was a similar project that was being done at NCSA that was presented at the Lustre Ecosystem Workshop in March. And it seems like it would be great if you guys got together and, got over the hump of, we both have early tools, let's combine the efforts. And also I think it's really important that things like this become visible to the community early on. So you avoid the duplication, but also put it onto, some links on lustre.org or something like that, so that, everybody knows of the good work that you're doing, right? And can leverage it.
Thank you. No, I did not know about the tool out of NCSA. Again, talking with Robert there's only so many ways to skin this cat. I'm not surprised that there was some convergent evolution, like sloths. They don't actually come from the same base. These tools, same thing. Is there a question over here? Somebody?
Thanks. This talk was one of the reasons I came out here, because we're about to start attempting our first backup of our Lustre system. And I guess just a quick question about, is there any minimum requirements? We're still running 1.8.9. Does it matter?
In the dependency tree, we do use liblustre API. There's a Python wrapper, and so I don't know, somebody else could answer this, whether or not liblustre API was supported in the 1.8 side, but no, if you look at the Python code, you see a bunch of LFS commands. And then you see some stuff going through liblustre API for particular needs. I suspect it probably was supported, and somebody could easily help you get it wrapped up.
Thanks.
Hey, have you considered using the HSM coordinator, treating it, and then you could allow users to request restoration?
So on the HSM side, we did consider it, but it was sort of like the changelog. This was easier for us to build and understand with the knowledge that we had without investing a lot of effort in understanding HSM, but that was one of the first things we looked at. But I'm not sure, I didn't quite understand your question about the frustration.
Restoration,
I'm sorry.
HSM restore, sorry.
Okay, so with...
You had me there.
All right.
Restoration, man.
Thank you. In that regards, if we were to do a restoration, it would be in the event of a catastrophe. So a restoration is not automated. This is not accessible to users. This is just a disaster recovery copy for our critical project data. So there's no automation there in that if we're going to do a restore, it's going to be a manual process with a lot of high songs time.
Sarp?
So we have a similar effort at Oak Ridge as well. We have been working on a user level tool, not a backup tool, but copy a portion of the data set from one Lustre file system to another. It's MPI based, so we'll touch base with you and the NCSA as well.
Oh, thank you. Yeah,
Compare the notes.
I knew that there was an MPI tool around, but as I said, I wanted kind of this dynamic scalable thing. This can certainly run in user space. RabbitMQ is just acting as a queuing system. We use memcache. It's a key value store. However you want to, many ways to sort of take that to-do list and have it get stored. And the nice thing is you probably have a nice fast interconnect. So the one client that's hosting the to-do list could use RDMA to actually populate the to-do list. Lots of ways to do it.
So Andreas, took the first part, which is, hey man, push that to lustre.org. Second part is yeah, you can do this with rsync. We did. My team lead is super awesome. We kind of cheated. I mean, we used a variant of NE2 scan to like feed rsync, you know, at least the first go around. It took forever. Man, this is really cool because we're going to be looking at doing this. I guess my question is, well, how long did your first pass take? I don't think you said. I mean, you said, well, you know, you can do a day.
I think, if I recall, about on the order of a week.
Okay.
So yeah, the background pass, give yourself some time. But the nice part is you can run it in the background, and how long it takes is really up to you and how much load you want to put on your production systems.
Right on.
So copying, the actual bandwidth part, low load, right? We're just streaming bytes. The metadata lookups, you want to balance. So I'd say order a week, and Haisong could tell you more specifically.
Okay, so about a week and then 3 days for
Synchronization.
A change, and then 1 day for
The delete pass.
deletes. Okay. Thanks, man.
Oh, you're very welcome.
Anyone else? Rick Wagner, thank you.